In this problem, we're going to verify that the Bohr model of the atom is consistent with observed atomic emission bands in the hydrogen atom by using the Bohr equation, the Planck equation, and the Rydberg equation. As a reminder, the Bohr atom of the model postulates that there is a nucleus and that there are discrete energy levels or orbits that electrons can inhabit, and it can only move between these discrete orbits. You can see over here energy levels of n-1, n equals 2, n equals 3, n equals 4, and they go on up to infinity. So we're going to go ahead and try calculating the energy that it takes to move between n equals 2 and n equals 4 and correlate that back to the hydrogen emission spectrum. In part A, we're going to use the Bohr equation to calculate the energy released when an electron relaxes from the n equals 4 energy level to the n equals 2 energy level. Because we're going from a higher energy level to a lower energy level, we're going to release a photon with a given energy. The Bohr equation is delta E equals minus 2.178 times 10 to the minus 18th joules times 1 over n sub f squared minus 1 over n sub I squared, where n sub f is the final energy level and n sub I is the initial energy level. In our case, n sub I equals 4 and n sub f equals 2. If we plug in our numbers, we get this equation, which if we crunch down, gives us a final answer of delta E equals minus 4.134 times 10 to the minus 19th joules. This is the energy of the photon that's been released by this electron relaxing. Part B. Use the Planck equation to calculate the wavelength of the photon emitted when the electron relaxes from the n equals 4 to the n equals 2 energy levels in a hydrogen atom. To remind you, there's our delta E from the previous page. The Planck equation is E equals hc over nu. We know E in this case, which is our joules we calculated in part A. C is the speed of light, 2.998 times 10 to the 8th meters per second, and H is Planck's constant, which is 6.626 times 10 to the minus 34th joule seconds. We do not know lambda, which is the wavelength. Therefore, the first thing we'll do is algebraically solve for lambda. Lambda equals hc over E. Now it's going to be easy for us to solve for lambda. We plug in and crunch all of our numbers. You'll note here that I've eliminated the minus sign from the energy value. That's because we just need the magnitude of it for this calculation. I've also thrown in the relevant units. Now, if you look at that units, you can see that both joules and seconds are going to cancel across fractions, leaving us in units of meters at the very end. We crunch those numbers and we get an answer of 4.805 times 10 to the minus 7th meters. If we convert that to nanometers, multiply it by 10 to the 9th, we get 480.5 nanometers. If we look at the hydrogen emission spectrum, we can see that there is a blue-green band right there at about 480. So we've been able to correlate this to our observed emission lines. For part C, we're going to use the Rydberg equation to verify that this wavelength results from a transition between the n equals 2 and n equals 4 energy levels. Remember, the Rydberg equation was empirically derived from the observation of hydrogen's emission spectrum. It doesn't have a theoretical underpinning. The Rydberg equation states that 1 over lambda, the reciprocal of lambda, equals the Rydberg constant, r sub h, times 1 over n sub 1 squared minus 1 over n sub 2 squared. We know that the Rydberg constant is 1.097 times 10 to the minus 2 invert nanometers, nanometers to the minus 1. N sub 1 equals 2. It always does when we use the Rydberg equation. And in our case, n sub 2 equals 4. We plug in those numbers, crunch it all down, and we get that 1 over lambda equals 2.084 times 10 to the minus 3 invert nanometers. we need to take the reciprocal, lambda equals 1 over 2.048 times 10 to the minus third nanometers. Crunch that, you get 488.3 nanometers. Recall from part B, we calculated from Bohr and Planck that it should be 480.5 nanometers, which is very close. Good luck on your Chapter 3 homework next week, and always come see me in my office hours if you have questions.